Thank you so much, everybody. We got there in the end. So, my name is Andrew Whitehouse, and I work for a consultancy called Wipro. My team's purpose is essentially technology consulting, so we help our customers end-to-end with a holistic technology vision. But we do focus a lot on quality engineering and test automation, and I'm sure you're all going to have an amazing day today, and you're going to learn a lot about technology and tools and utilities. But I want to talk to you a little bit about maybe something a little bit different. Maybe something that you can all take away and apply at your different organizations, within your teams, that may help you to think a little bit differently about the way that you do testing. And that's the idea anyway, so we'll just see how we go. But first I want to talk about refrigerators. These are fantastic devices. We all have one. We'll all probably own several of them in our lifetimes. But they're absolutely amazing appliances. And if you didn't know, this is actually how your refrigerator works. Essentially, in the enclosed environment that you have here, that is a refrigerator, you have a small system that's driven by a compressor. And essentially what the compressor does is it pumps cold liquid gas through what's called evaporator coils that stretch all the way throughout the interior of the refrigerator. And then those evaporator coils, they actually remove the heat from the air inside the system. And then they pump that hot compressed gas out through dissipation through the rear of the refrigerator. And, probably if you've ever tried to move your fridge, or, perhaps if you're moving house or trying to defrost your refrigerator, you would have noticed that it's quite hot if you've stuck your hand behind. And that's essentially what the heat exchange process is here, which is not too dissimilar to the way that a split system air conditioner works. So it's quite cool, actually. Yes, fridges, they cool things. We put our groceries in, we put our drinks in, we chill things down. Yes, that's what they're for. But what is it that's actually happening here inside this environment? What is it that happens when we cool down an enclosed space like this? Well, given the right conditions, water vapor comes from the air. And, given the right relative humidity, we can actually get to the dew point where water vapor collects. And quick question, can anyone here tell me, and by the way, this is the question for the prize, can anyone tell me what the 3 forms of water can be? Somebody yell it out. Not all at once. Everybody gets a prize. So yes, gas, liquid, and solid. And so water's amazing in this way, right? It's the only substance that can really take on all 3 forms of matter. And since water can be in 3 forms, there's a lot more going inside your refrigerator than it might seem, than meets the eye. And in respect to that present water vapor that I was describing, that's what I want to sort of focus on here in respect to refrigeration. And it's really important that when water moves from its liquid state to its solid state, that's going to tell us something about the way our refrigerator operates. And so, why does any of this matter? Why is it important? Yes, fridges are cold. We store our beer in them. It makes the beer cold. End of story, right? Well, the answer is kind of on this slide, and it's not this ice cube, although that ice cube is pretty cool to people of my generation. It's this ice cube. And that's essentially what matters here. And, none of this would be a problem if we were talking about a freezer, but we're not. We're talking about refrigeration. We don't want things to freeze, and in a cold environment, we have that possibility. Again, given relative humidity, given water vapor in the air, water can collect at that dew point, and unless you want ice inside your refrigerator, that's actually a bad thing. And this is a picture of my actual refrigerator, and I'm chipping sheets of ice out of the bottom of it with a spoon. which is bad, obviously. This shouldn't happen, right? We're talking about refrigeration. So, but surely you would ask yourself, refrigerator manufacturers, surely they've come up with a way to deal with this, right? I mean, this is a common appliance. It's been around for a long time. And surely this is something that they've thought of. Surely, right? Well, of course they have. And there is a system in place to be able to deal with this exact scenario that I'm going to describe for you now. And if you've ever opened up your refrigerator, you've probably seen something a little bit like this. There's a panel in the back with a fan for circulating some of that cold air. If you were to take that panel off, you'd see those evaporator coils that I described earlier, and you'd see a small system there that's set up exactly to deal with this problem. And what that system is it's made up of 3 different components, and one component is a drain heating bar, which supplies a small amount of heat. And that's situated over a drain pipe or a catchment area for catching that errant water or water vapour. And these two are connected together with what's called a drain strap, which through a heat exchange process supplies a small amount of heat to that system. And this is essentially how refrigerator manufacturers have set up a system to deal with errant water or water vapour within your refrigerator. So just to summarise the system, right, we've got 3 components. We've got the drain heater, the drain strap, and the drain. Now, how does this fault occur? Like, how did I get myself into a situation where I had to chip ice sheets out of my refrigerator with a spoon? Well, sometimes what can happen is that errant water that collects through its vaporous form into liquid sometimes bypasses this catchment area here, and it drips into the bottom of the fridge. And then, given the right conditions over time, that can also freeze. And this is also generally where refrigerator manufacturers put their vegetable crisper, in the bottom of the fridge, where it's usually the most cold. And so frozen veggies, right? I mean, that's how you get into that situation. But surely, how can this happen? I mean, there's a system in place to deal with it. We've already discussed that. How can this even occur? And of course, I'm not going to name and shame any manufacturers here, but I'm just going to strategically place these pictures here of Uncle Sam and Sung Kang, the actor from Fast and the Furious. That's Uncle Sam and Sung Kang. Yeah, if you can pick up what I'm putting down. So, I mean, what happens when a product's in the field and there's an error like this? Sure, it's in the hands of consumers. I mean, what is it that happens? Well, I'm at a testing conference, and we all know what happens. Somebody from the business comes down, and a tester's heart sinks when they hear this phrase, "Get me the testers, I want to see what you tested." We've all been through this before, and at that moment when that happens, we think to ourselves, oh my God, what did I forget to test? If we only had another 10 test cases in the regression suite, we would have been fine. Well, I'm guessing probably what they tested in this mythical QC process that I'm postulating about here. Of course, I don't know what they tested, but I'm guessing it's probably pretty standard. I think it's probably pretty similar to what most of us in the testing industry would have done. I'm guessing they probably looked at, potentially some isolated tests. You might even refer to these as unit tests. And they probably checked a whole bunch of things in isolation. They probably checked that the heat bar produced heat. They probably checked that the drain clip was the right shape to join the 2 entities together. They probably checked that the drain clip conducted heat or had current. And they probably checked that the drain was able to carry away water. This is all pretty standard kind of isolated unit tests. And then probably what they did is some sort of integration test. They probably joined everything together. They probably set up the environment. Maybe even they sprayed a bit of water vapor in there, shut the fridge, switched it on, and waited to see what would happen. And this is a pretty standard scenario-based test, right? A pretty standard end-to-end test that most of us would write. So if all of this worked, how did we get ourselves into the situation where we've got ice in deployed refrigerators in production? Well, to understand how things went wrong, we need to talk a little bit about systems. But what even is a system? And what I would term as a system is units of functionality, or groupings of units of functionality that are all connected together to perform procedures, processes, transactions, essentially interactions. And really, if you think about it, a system is really just the sum of many entities collaborating together to achieve an outcome. But what's important in a system is what defines those interactions. And entity interaction, typically should be, and I say should be, defined by what we generally refer to as an interface. Now, it's not these individual isolated units of functionality or individual isolated components of functionality that actually matter. It's the interface, it's what defines the way that they should behave together in a unified system. And this is essentially what dictates the behaviour of any system that you would work with. Now, if we consider this for a minute, can we apply this to our refrigerator drainage system? Well, we kind of just review what's in our system here. We've essentially got three components, or if you like, two components and an interface. And if we take that a step further, really what you have is you have a service provider and a service consumer joined together by an interface. And since we know that it's the interface that dictates the behaviour of the way that different component entities behave together, can we perhaps ask some more questions of this particular system to try to discover how things actually went wrong for this particular model of fridge? And, interfaces are critical. They help system entities to define their behaviour up front and to design their behaviour up front. And really what an interface does is it lets you ask two questions. Can you provide something? Is there some service that you provide me? And given a particular situation, what is it that happens? And if you put this a slightly different way, essentially all this is this is behaviour and this is a contract. And so when we were talking earlier about, in our mythical QC process here, potentially what did they test? Surely the end-to-end scenario would have worked, right? I mean, that's a pretty standard way of testing. You build a system, you put all the component parts together, and you run a scenario test, right, end to end. Well, things tend to happen when we assume correctness in a system. Often the way that we configure a system or the way that we set it up that dictates the scenario we want to run can hide things about what's happening underneath in those component entity behaviours. And if we don't have a firm understanding of how those component entities are supposed to behave at the lower level, then those problems just move up the stack and they increase in complexity. However, though, this changes when we focus on testing system behaviours or defining those system behaviours through interfaces or interactions. And when we analyse this, when we think about the way that entities should behave together in a component system, things start to become a lot clearer about the expected behaviour. And now in our three-component system here, where we've essentially got a service provider, which is the drain heater, and a service consumer, which is the drain, the service consumer can ask the question, do I know whether the provider is able to supply enough heat for my specific needs? And this actually prompts the producer to say, well, do I know whether the consumer's needs are met based on their interactions with me? Essentially, am I validating my consumer's needs? And when we think about entities in this way, it actually informs their design. And again, right, consumer informs provider. And our consumer here can ask that question could a situation arise where the volume of water that I've collected is greater than the drain heater's ability or the drain strap's ability to stop it from freezing or draining away? And the provider in this instance can say, because I know that a situation like this could occur, I need to accommodate that behaviour into the design of my service or the functionality that I provide. And this back and forth, this consumer asking a question of a provider, we formalise this. We formalise the interaction itself by writing tests. And when we do this, when we explore those interactions and formalise them as tests, we reveal potential faults. Faults that, as I mentioned before, as they move up the stack, become more complicated and can be hidden in the system configuration itself. So in our drainage system here, a situation can arise where the volume of water in the drain reaches an escape velocity where the heater's ability to stop it from freezing, the drain strap's ability to help it to drain away, basically cause it to freeze. There's too much water there, and in the right conditions, when it's cold enough, basically the strap can't conduct enough heat to keep that liquid water moving, the drain freezes, and then essentially any additional errant water that does drip down will simply just drip over the edge. Gravity will take it into the base of the fridge, and that's how I got myself into the situation. It's very messy, by the way, and very inconvenient to have to constantly throw away massive amounts of frozen vegetables and then chip ice sheets out with a spoon. But if we'd considered this up front, could we have designed a better interface? And essentially, this is what it's all about. I mean, this is true design-driven testing. When we think about interactions fully in this way, we can come up with better designs in the first place. And because as testers or, as system designers or system engineers, we can't foresee all possible scenarios up front. And so, therefore, what we need to do instead is make sure that we can enact the best possible design by thinking about the behavioural interactions of components within our system up front. And we use those tests to inform the design. So just to quickly recap, so instead of just connecting component entities together and assuming an outcome, applying the configuration and the setup that we feel is necessary, for perhaps some high-level requirement that somebody that didn't build the system came up with, we design our interactions or our expectations by formalising them through tests. We ask certain questions of components within the system, if those components are service providers or service consumers. And typically within a system, even if you're a leaf node, you're going to have consumers. So nothing exists in isolation. And we do all of this with a more optimized form of test. So let's talk a little bit more about those tests. But before we do, really the point that I'm trying to make here is that the needs of the consumer or the needs of the individual component only become apparent when we start defining interactions through this way, by properly testing an interface and properly driving its design. And of course, in the case of our refrigerated drainage system, of course we can fix the design flaw here if we think about things this way. And really, in this instance, what was required is a better interface. We needed a drain strap or a drain clip that allowed enough heat to be conducted so that given that situation where the drain was full of water, it wouldn't freeze. And we also needed it to extend far enough into the drain to allow that water to drain away faster. And when we do this, when we implement this new interface, essentially ice water can never form from droplets from vapour, become liquid, and under the right conditions, freeze. So, in case you're actually wondering, this was the actual issue, and this is the replacement part or interface that the manufacturer released. And I didn't actually keep the original one, but it was a tiny piece of metal, and it's obvious that it was never going to work for its intended purpose. But you know, often retrospectively, when we start to think of things this way, it can seem obvious that an interface or an implementation wasn't correct retrospectively. And by the way, I installed this myself, and everything works perfectly now, which you'll be very glad to know. So, summarizing this issue, right? Well, we tested a whole bunch of parts in isolation, and there was no issue. We did some pretty typical scenario end-to-end testing. You know, again, everything seemed to work, there was no issue. But the real problem here, the real crux of this, is that the behavioural outcomes themselves, the very ones that we've been interrogating, didn't maintain integrity over time and at scale. Things were hidden about the way that they were going to behave together that weren't only revealed at scale or in production in deployment. And really the learning here is simply that for us to understand a system properly, we need to decompose it. We need to break it down into its component parts. And really system interactions should always be defined through an interface, whether that's a formal interface or that's something that you create through expectations by formalizing that in test cases. And in the situation of our refrigerator drainage system, a scenario occurred here where over time, the individual components weren't set up to handle. And the problem is, for us as testers, that these first two methods of testing were never going to reveal that fault. In the system testing scenario that we described, we were never going to find the fault unless we properly interrogated the interface. So, how can we do better? And I mentioned potentially different forms of testing. Well, what we need to do in principle is apply our thinking about system behaviour, apply this methodology, right? The way that we think through how component entities should interact. We need to apply that by using tests to drive the design of those component behaviours. And so this is where I want to propose a couple of new test types. And this is how we're going to formalise and codify those expectations that I mentioned. And initially, those two tests are going to be the contract test and the collaboration test. And so what is a contract test? Well, its purpose is to check the structure of the behaviour between two entities remains the same over time. Essentially, is that agreed contract or that structure, does that remain acceptable given changes? And a collaboration test, well, its purpose is to check that the behaviour of an interaction plays out as expected when requested. So as a service consumer, I need to check that any behavioural outcomes that I expect from my service provider or my neighbouring component in the system is carried out. And essentially, all we're talking about here is system structure and system behaviour when you boil it down. And so, with this in mind, how can we use contract and collaboration tests to reveal some of these sort of lower level faults that I've been describing? Well, there's essentially three ways. With a contract test, what we're checking for is structure. And with a collaboration test, as I mentioned, we're checking for behaviour. And then with an integrity check, what we're doing is we're making sure that that behaviour is maintained over time and at scale. And you can think of the approach like this. We pin our structure and our behaviour with contract and collaboration tests, and then we execute those at scale over time. So what does any of this have to do with test automation? I know that's the title of the talk, but if you think about it right, designing what to test is absolutely the most important thing that you could do as a tester. And this is critical before you dive in and grab the latest tools, build a framework, write code. The absolute most important thing you can do as a tester is think about what is it, what's the underlying behavior that I'm trying to pin here? What's the purpose of my test? What is it that I want to interrogate within the system so that I can make sure that over time I can monitor that nothing goes wrong or that changes don't have an impact? Well, the point here is that it doesn't matter what system we're talking about. I mean, I've been alluding to manufacturing and appliances, but really this applies equally to software. It's different technology, but the players in the system are exactly the same. You're still dealing with component entities that are put together, that collaborate together for a specific outcome. And I've got countless examples of this happening to me as a professional tester in the real world. And I'll describe some of them for you, and it'll become apparent just how similar this is. And in the example we had earlier around the refrigerator drainage system, we had 3 components or 3 entities, right? And if you took our drain heater, but instead it was a web service or an API, and you took our drain, and instead of that you had maybe a SQL Server database, a relational database, that were connected together through an interface. Well, I've had this scenario in a production system before. And essentially what was happening here was we had a web service that was running a query on a database, and it was using an inversion of control container to basically create a data layer or an abstraction. SQL Server was opening a client connection, running the query and responding back to the caller. Fairly simple, right? And as you could probably guess, the scenario test in that example worked perfectly. The end-to-end test worked, no issue whatsoever. But what happened in production was the ISC container wasn't properly terminating those SQL queries. But we would never have known that in the end-to-end integration test because we hadn't interrogated the individual components themselves. So obviously, the logical conclusion here is that we had a memory leak, the server blew up, and that's essentially what happened. And if you think about it right, in this example, the unterminated queries, those SQL queries that were never closed off, are the ice that blocked the drain. And so history really repeats itself here. And as we sort of talk a little bit more about these contract and collaboration tests, we'll see just how important it is to interrogate those lower level behaviours. But not only that, to check them at scale. And that's where the integrity comes in. So let's look at a couple of examples so that we can understand a little bit more about the roles that these different tests play within interrogating systems. And if we want to use contract and collaboration tests, if we know and we all agree that we can't rely on end-to-end tests completely, here's a simple way that we can use to apply them in component systems within software. Well, the first thing that we need to do, as we know, is check the structure. So we need to check that the structure is maintained between component entities through an interface. Is it as agreed and is it maintained over time? And the second thing that we need to do is to check that behaviour. We need to think about, as a consumer of a service or as a provider of a service, am I maintaining the behaviour that I either functionally expect or that my consumers expect from me? And essentially all this is given a situation, what happens, what plays out. And the final thing that we need to do here is check that behaviour at scale. So again, this is just component interactions, but we're checking them at scale over multiple threads under load. And so if we think about that, again, as we were discussing techniques for testing, instead of just trying to guess what we should do, we really need to use the system at its component form to inform us of how we should write tests. We actually dictate the behaviour of how systems will behave at their component level, and we prompt service providers and neighbouring components to adjust their design to suit our needs. And in any given situation, a consumer always needs to ask the provider, do you maintain or carry out my expectations? And as we do that, using some of these new testing types, it becomes apparent what needs to happen. Again, right, from a consumer's perspective, the contract is just simply checking the structure. And a consumer can use that to make sure that, over time, given I know that there's going to be a lot of adjustment, there's going to be a lot of changes, surely I'm not the only consumer or component within a system. And so that interface or that specification is constantly changing, it's constantly evolving. And that's where we use the contract test to pin that structure and make sure that, as it does change, when it will, that it doesn't impact us. And subsequently, the service provider itself can use the contract test to check that certain properties or elements within the current agreed contract or current agreed structure, when they do change, don't have knock-on effects downstream. And the collaboration test, again, within the life cycle of what a consumer is trying to do, again, it's all about behaviour, right? It's all about functional outcomes. And what we do with the collaboration test is we inform the provider what the behaviour should be. We actually say, this is how I intend to use your service. And given I've formalised that in a test, then through that interaction, through asking questions, the provider can understand how they need to design their system. And they can design it in a way that accommodates you as the consumer, as well as multiple other component entities within a system. And again, all of this needs to fit into our integrity methodology or integrity framework. It's not enough just to check the behaviour, although you can think of it as the collaboration or the behaviour is how to set up the design, and the integrity is what makes sure that it happens at scale. And so, as consumers, we always want to ask, what happens if I do this multiple times? What happens if I'm doing this at scale? What is my actual expected usage? And that then prompts the provider to say that, okay, since I now know what volume you expect, then I can adjust the behaviour of my service to accommodate your needs. So, with this type of testing, and you've probably guessed by now that most of this is fairly low level. It's not linked to specific implementations. We're not talking about screens. We're not talking about elements. Really, it's difficult for me to show you specific examples in the context of a presentation, but I will try to show you some pseudo examples, and I've got a GitHub repository that I'm going to share with everyone as well that's got a whole load of examples of contract tests and collaboration tests for you to have a look at in your own time. But basically, I like to think of contract tests as alerting and monitoring for consumers and providers within a system. And that's really what their purpose is. Again, what we want to do is we want to check that any changes to the existing contract or interface, we want to check those against a known good version, something that we expect and that we can measure over time. And again, a provider can use this to validate if any specific changes to that interface will affect their downstream consumers. And providers do this in many different ways. But if you think about a service specification, perhaps an API or a web service, then we can check our underlying primitives or our properties to make sure that, given my consumer is probably on a different language stack, what happens? What do primitives mean to them in their language? And does making a change at that point, is that a breaking change for that consumer? And this is actually a really good indication of how things will play out when we do make changes to the interface or the structure. And it gets you a lot further than you might think in terms of completeness of a testing approach. And in my kind of semi-pseudo JavaScript code here, essentially all I'm doing is I'm capturing a known good version of the contract or the interface. You know, some sort of artifact that I can version control somewhere and rely on. And then any change that's made to that interface or that contract, I'm triggering a test to go and fetch the new version and simply compare the two. And that can tell us a lot. And really, what I like to think about this is it's a conversation starter from consumers to providers in a component system. It's a way to start the conversation and say, given you made a change, how does that impact me? And in terms of collaboration tests, well, again, collaboration test purpose is to check that within the life cycle of what a consumer expects, the behaviour that they expect from their service provider, is that maintained and carried out? And essentially what you can see here is that as a consumer, I'm checking several properties about a query. I'm checking that it was run. I'm checking that a connection was closed within that query lifecycle. And I'm doing it all under load. Again, this is the integrity part of the behaviour. And again, right, as consumers, we don't necessarily care about underlying implementations. We don't necessarily care about how things are implemented. That's the provider's job, right? That's abstraction. But we can still check that in the life cycle of what we want to do, given a certain functionality is called, is that carried out? And that's the best you can do in that situation. Okay, so contract and collaboration tests, I mean, we use these as an executable way to define behaviours within a component system. And as you can imagine, the more that you do this, it just moves up the stack. And again, the purpose here, right, is to give functionality providers or neighbouring components in a system insight about how we're going to use their functionality. And it helps them to design better functionality, better services. Okay, so at this point, I'm hoping that this is kind of starting to make sense, right? I mean, systems are complex, they're difficult to break down, but when we think about it, all that matters is the behaviours, the underlying behaviours within our systems, right, within our component systems. We all deal with systems daily, but usually we're thinking about holistic scenarios. Usually we're not thinking about component level scenarios. And when we start to apply this thinking, in our day-to-day work as testers, really interesting things start to happen. And I'll quickly describe some of those things before I finish up, but just to address really quickly, because I'm sure that a lot of you are probably thinking, this is a nice methodology, it's a nice way of thinking, but it won't necessarily work in the real world. Well, I'd love for you to come up and have a discussion with me about that, and happy to share my experiences. But essentially there's a couple of situations where this might be difficult to apply. But if you're dealing with perhaps off-the-shelf software, or you're in an environment where you don't necessarily have your own engineering team, you're still accepting code, right? You still have integration points. And that's where you start the conversation about system behaviour, about how a vendor's software is supposed to behave when integrated to yours. Now, in terms of more legacy environments, I mean, this is a fantastic way to start your journey to decomposing a bigger system, a more tightly coupled system. And this is a way that you can take your engineering team on a journey. Hey, look, I know a lot of us don't have time to really sit back and pick systems apart and fully interrogate every interaction, right? But as professional testers, we have a duty to set up our engineering teams for success. And if we just put in a little bit of extra effort, perhaps an hour a day for a couple of days a week, you can really get yourself quite quickly to a stage where you bring your entire team or your organisation on a journey with you. And you use these techniques to make the designs, the underlying interactions in your system, much more robust. And just quickly, I mean, if you think about these tests inside a release pipeline, right, your typical sort of build pipeline, I mean, usually most of us are dealing, you know, even in the test automation world, we're dealing post-deployment, post-artifact deployment. But when we're talking about contract and collaboration tests, again, we're not linking ourselves to underlying behaviour. So most of these tests just, they run in memory. And so this is the level we're operating at here. We're running these tests in milliseconds, or at least minutes, as opposed to, you know, post-deployment tests, which usually take hours or days. And if you think about the impact that that would actually have on the feedback loop, your ability to make a change and stay within the context of the change you were making, it's pretty powerful. Okay, so just in closing, there's an implication here of what happens. You know, if you're able to carry all this out perfectly and apply all of this to your own systems, there's something that actually starts to happen, and I'd encourage everybody to do some research on this. But as you start to truly drive design into all the neighbouring component entities within your system, those component entities need to externalise certain things about the way that they design their functionality to make it easier to supply a service to you, to make their service more testable. And as they externalise those things, perhaps they have to do with, you know, transportation or data sources or networking, you start to get what's known as hexagonal architecture. And this is something I'd encourage you all to investigate, because it's really, really cool what happens when you start to get to here. So thank you so much. As I mentioned, I'll share some examples of contract and collaboration tests on my GitHub. And I hope you all have an absolutely fantastic day.